Hello A2A and welcome to Chapter 2. So this first section, we're going to look at the transformations of quadratic functions. And this whole chapter is going to be about looking at quadratic functions and their equations and how to graph them. And Chapter 3 will also continue more into quadratics as well. So we're going to spend a lot of time with them. So what I thought it might be helpful to do, we're going to talk about your parent function. But let's first, sort of down in the middle of the page, I've set up this grid, this XY coordinate grid, and I thought we should look at the parent graph. And then we're going to look at a particular form for a quadratic, a parabola, which is what we call the graph. So if I plug in some values, if I plug in 0, I'm going to get back 0. So your quadratic parent function always has a vertex here at the origin. If I plug in 1, 1 squared is 1. So I'm going to graph, you go over 1, up 1, and what you're going to find is a parabola is always symmetric, and that makes graphing it really nice. So that means on the other side of the y-axis, I can go back 1 and up 1. And then if I want to graph when x is 2, well, 2 squared is 4. So this was at 1, 2, 3, 4. So I'd go over 2, up 4, and I would use that symmetry to graph it over here. And then just for the sake of getting a little more, if I take 3, 3 squared is 9, 5, 6, 7, 8, 9. That would put me way up here, and I can use that symmetry. So this is what your parent function is going to look at like. And what we're going to do is we're going to look at what's called the vertex form. Vertex form is this right here. And what is nice about that, and again, a is not going to equal 0 because that would just be silly. We'd have no graph. This is a form that shows us when we look at it, we can see the vertex. The vertex is going to be that HK value. So you can see in the parent graph that would be 0, 0. And the symmetry of the graph means that there's always a line that runs through the x coordinate of your vertex. That's always going to be the line x equals h. And we're going to use that so you can graph both sides of it. And that line of symmetry, or axis of symmetry, it divides it into a mirror image. All right, so we want to look at what happens when you translate and dilate this form of your quadratic. So let's first look at what happens. Notice how there's this a value in front of everything. So if a is positive, your graph is what I call a smile. So this is if a is positive. If a is negative, then we can call it a frown. So this would be a is negative. It's a reflection over the x-axis because it's outside the function, so it's taking all the y values. It's like a vertical reflection. Then we're going to look at the values of a, how that affects the graph. Well, if a happens to be a positive number, so greater than 1, then it's going to be a vertical stretch. So when you are doing a vertical stretch, you can see that it's going to be the y values that get multiplied. It's like if you stood up and pulled taffy, or you stretch your arms up in the air. That's a vertical stretch. The y values are getting longer. If your a value is between 0 and 1, that's going to be a vertical shrink. So you'd be multiplying those y values by a fraction, which actually makes your graph a little bit wider here. It's going to shrink you closer to the x-axis as opposed to the stretch pulls you away from the x-axis. Then we have our horizontal stretches and shrinks. So these are going to be your dilations. Now, horizontal are always going to act counterintuitive. They're always going to act the opposite of what you would think. So if what you see is a b value that is greater than 1, that's actually a horizontal shrink by a factor of 1 over b. So a horizontal shrink, now this is horizontal, that's in the x direction, so you're multiplying your x value actually by 1 over b. We'll talk about this more when we're actually having to do these. Right now you're just going to kind of get an intuitive sense for them. Now if my b value was between 0 and 1, that's actually a horizontal stretch. So that means that b is a fraction, so it's actually going to move you further away. You'd be multiplying by the reciprocal of that fraction, and it would stretch you away from the y-axis. And then the last one we have, which we don't usually see, is if b is negative, you would reflect over the y-axis. Because the parent function already has symmetry here, you're not going to actually see this. So all of these points would reflect over to the pink points, and all the pink points would reflect over the blue points. But since there's already symmetry there, you wouldn't really see it. Okay, so those are the dilations. Then we get into our translations. Translations are a little friendlier because they do not change the shape. They basically just pick the graph up and move it one way or the other. So again, if it's inside the parenthesis, like this b is inside the parenthesis, x minus h is inside the parenthesis of the something squared, it always acts the opposite of what you would expect. So if you see x plus h, even though that's a plus h, it's going to move you in the left. So that's going to move you in the negative direction. So that will shift you h units left. So that would be this one. So my new vertex would be here at x plus h, or plus h actually is where my vertex would be. Now, if I saw x minus h, that's going to shift h units right. And so that would be over here. So this would be h, and let me go ahead and correct this. This would be at a minus h. So it's actually x minus a negative h when you're going back in the negative direction. But it always works opposite horizontal as you see it. Vertical is the friendlier one. Vertical is this plus k. Notice it's outside the parenthesis. Anything outside always acts exactly as you see it. So plus k means you're going to go k units up. So that would put me up here. And if I saw minus k, that would shift me k units down. They do not change the shape of your graph. They just basically pick it up and move it up and down, right and left when it's a translation. Dilations, vertical, you multiply the y value to get your dilation. Horizontal, you'll always multiply the x value by the reciprocal of what you're trying to do. But that's getting a little ahead of ourselves. Okay, so let's look at these down here and see if we can describe what's going to happen to the graph. So I see inside the parenthesis, I see x plus 4. So that is going to shift 4 units in the negative direction, which is left. And then this minus 1 is on the outside, so that is going to shift 1 unit down. So it does exactly what you would think it would do. In example B, again, inside the parentheses is horizontal, so that is going to shift 1 unit in the, I'm bad with my right and my left. 1 unit, that's why I always say in the positive direction, which is right. And here we have the +2 is outside the parentheses, so that is going to shift 2 units up. And then down here in example C, we got a little more going on. Notice we have an A that's negative now, so that's going to reflect over the x-axis. And the 1/2 is also outside the parenthesis, so that's going to be a vertical dilation, and let's say a vertical shrink by a factor of 1/2. Then inside the parentheses here we see a -3. Let me do that in a different color. So -3 is going to shift us 3 units right in the positive direction. And this last one is the +2. There's a lot going on in this one. That is going to shift up 2 units. Okay, so anything inside that parentheses is horizontal. Everything on the outside is vertical. So here, there's nothing inside any parentheses. So the 2 is going to be a vertical stretch by 2, by a factor of 2. I'm okay if you just say by 2. It's understood it's by a factor. And this +1 is going to tell me that we are shifting up 1 unit. All right, so you guys are going to do a little activity with Desmos where you're going to be practicing this.